This is CPE 133, Chapter 13 of the Free-Range Verilog Foundation Modeling text. This chapter involves behavioral modeling of finite state machines, of course using Verilog, and this is the first lecture in a series. The disclaimer: you gotta actually break down and generate some circuits, model some circuits in order to learn Verilog. You're not going to learn it by watching these boring videos or by reading the text. You got to actually generate some problems, generate some errors, fix those errors, and that's where the learning takes place. So finite state machines are essentially a circuit that controls another circuit, and these are, so I call it a controller circuit. So these are essentially all digital stuff as well. So it's kind of, usually you get into it at the end of your beginning digital design course, and it's actually it's a really useful topic. Besides being really interesting, it helps you tie everything together, and particularly allows for you to create some meaningful designs. Typically, when we're dealing with state machines, we start with a state diagram. The state diagram models what the state machine does. Now, the state diagram is kind of a language of its own, and it has a special symbology that the more you use it, you'll get used to it pretty fast. It's not that complicated. The good thing is state machines themselves used in many engineering disciplines and computer science as well. So the approach we're going to take is to model finite state machines at a relatively high level using Verilog. So the notion of modeling state machines using Verilog, it's actually very cookbook, and it's not very engineering. It looks horrendous at first, but it's actually very, very straightforward. Realistically speaking, the engineering step is generating the state diagram for your circuit. Another engineering step is, of course, just generating your circuit. And remember, we're generating our digital design such that they solve a given problem. So the approach we're going to take essentially leverages your knowledge of both sequential circuits and combinatorial circuits, and particularly how those circuits are implemented in Verilog. Plus, it's just you got to be able to design a basic circuit and able to control the circuit. So this is our standard FSM model at a very high level. It's broken into 3 boxes, which is next state decoder, the output decoder, and then the state registers. Now the 2 decoders are, of course, the decoders, so they're combinatorial, and then the state registers are sequential. Now the issue of general high-level state machine, you've got external inputs coming into this thing, and the notion is that these are status inputs from other parts of the circuit. So these are status input for the state machine. State machine is going to interpret those, do what it needs to do, and then output these external outputs. Now these external outputs are used to control other parts of the circuits. Okay, so here we go. As far as the outputs go, there's 2 types. There's mealy and more outputs, and we'll talk more about that in a second. So we're not gonna use this model here in Verilog. What we're gonna do is combine the 2 decoders into one circuit, and that's going to be a combinatorial circuit. So the issue is this new combinatorial circuit, which is this thing right here, is going to handle the calculation of the next state, and it's also, you can see it right here, it's also going to determine the outputs. And so these outputs are right like that. Those are the common outputs. So here's the next state right here, and here's the outputs. This sequential circuit is going to hold the state values, which is the state registers. It's also going to process any asynchronous signals that are present in there. So there's your asynchronous signals. You can see whatever your external inputs also going into. It's actually the next state decoder and the output decoder, but we've combined them here. And so that's a little bit different. It's going to simplify our implementation of state machines in Verilog, and particularly what this is going to allow us to do is put one always block for the sequential part of the circuit and one always block for the combinatorial part of the circuit. So this is our super contrived state diagram. Doesn't do anything. I tried to put a little bit of everything in there just to make it somewhat interesting. So anyway, so we're just going to grind through this, and quite frankly, look, I I can't remember how long it's been since I designed a state machine. Anytime I have to model a state diagram, I start with a template. The template has most of the stuff there, and that's what I expect of my students, just to be able to work off the template. Certainly not memorize anything. So a couple steps to the solution in this thing is, number one, make sure you have a state diagram sitting in front of you. Don't try to wing it and skip the state diagram part. Generate a state diagram. Second part is just to take a look at the state diagram and analyze it and see what's going on. And then in particular, the third step is you want to generate a black box diagram. So let's do that. So we can see here and here that we have three states. Obviously, there's three state bubbles. We have an asynchronous input. We know that because the input's coming in out of nowhere. As far as output goes, it looks like we have a Mealy output and a Moore type output. Pretty standard there. Good names on those. And what else? Inputs here, and I only see one input, so there's just one input, which is XN. So here are the two outputs. Here's the input. Here's the asynchronous input, and here is the clock signal. So the first part of the solution is to, of course, encode the external interface, which we do there. We clump it all in one line just to save space. We toss a underscore n attached to the reset, such that it kind of gives a self-commenting notion that the reset signal is active low. So what we're going to do here is first is define our state variables, and so we're just arbitrarily going to define two state variables. Now the width, which is PS, and NS, which is present state and next state. The width of these is arbitrary. We need at least 2 bits because we have 4 states in this state diagram. So that's the state defined. But now what we're going to do is define some constant values to represent the state registers. And so we've given ourselves three constants here, but we also assign the constants of value. Those values there are the actual values of the state register. And if you notice that they're all 2 bits, and they are all different. They're all unique. There's going to be 2 always blocks in here. The first one has to do with the sequential circuit, and so that's this one right here. But that sequential circuit does 2 things. It assigns the NS to PS, but it also handles the asynchronous inputs. This is just a typical always block here. We've used the pause edge and neg edge in here. The neg edge is associated with the reset. And you can see it's active low based on the fact that I am looking for a neg edge and the resultant value to be 0. Once again, it is an always block, and by the notion that I use the pause edge and neg edge in the sensitivity list, any value that I assign in the always block is going to be a register. So the only thing I'm assigning in this always block is PS. So PS is going to represent the state registers for this design. As you can see, it is a sequential design, which is why I use the non-blocking operators in this. This is a partial solution. It's just encoding state A plus some other stuff. But this is the always block modeling, the combinatorial process. So what I've done in here is put 2 variables for the sensitivity list, which is the input and the present state. I should have just put an asterisk in there, not worried about it. Now the first thing you want to do in the combinatorial process, because the combinatorial process is responsible for assigning the outputs, I want to ensure that the outputs always have a value. So I take all the outputs and I assign them just some neutral value. Now this is essentially kind of a default value, kind of sort of, but we'll talk more about that in a second. So every output is assigned. I do that for one reason, which is to prevent latch generation. This is a decoder. I want it to be combinatorial. I don't want a latch. The next thing I do here is I have a case statement that looks at the present state variable. Actually, there's going to be one case clause per state. What we're looking at here is the case clause for state A. So when the PS here is in state A, which, state A is just a constant, I want to implement what I see there. Now the asynchronous input is part of the sequential process, so I don't have to worry about that. But what I see here is a xn doing two different things. When xn equals a 1, it stays in state A. When xn equals a 0, it goes to state B. So here it is. In state A, I turn the more output on. That's the first thing I do. So anytime I'm in state A, the more output's a 1. Next thing I do is I handle the transitions and the Mealy output. Now, the transitions and the Mealy output are based on the external input. So here it is. If x is a 1, the Mealy output's a 1, and the next state is A. X is a 1, the Mealy output is a 1, and the next state is A. So that encodes this transition arrow. And then else handles the other one, which is the next state is state B, and the output, Mealy output, is also a 1. Now, since this Mealy output is a 1 in this state all the time, I could have put it up in there just to shorten the code a little bit. It doesn't really matter. Now, the issue in this state machine is that if you look at it, both the more and Mealy output have been reassigned after I originally assigned them, and this is okay. It's typical. You're expected to do that. The idea here is this assignment was never made. It was scheduled to be made, and it doesn't actually get assigned until this always block terminates. So when the always block terminates, it only accepts the last assignment it saw. So in these two cases, it would be the more and the Mealy equal 1. It wouldn't be the old version. So state B, a little bit more simple than state A. The issue is in state B. This is state B. It unconditionally transfers to state C, and that's what you can see here. So when I'm in state B, the more output's a 0. Here's the more output's a 0. The Mealy output is a 1, and it unconditionally transfers to state C. So even though I know this is a Mealy type machine because it has Mealy outputs on it, I don't need to put a conditional in there. The conditional is associated with the if, else statement. I don't have a conditional because it unconditionally transfers from state B to state C. So this is the complete solution. I actually did my best to kind of squish it together and fit it on one page. I know it's pretty small. The issue here is this is a case statement. It does in fact have a default in there. The issue for a state machine such as this that's not completely defined, meaning there's an extra set of bits that we didn't use. This default actually acts like a catch-all. So this is your catch-all, kind of makes your state machine self-correcting. So it's actually pretty important. The issue is that anytime I don't have a catch-all in a case statement, I think to myself, wow, that's a sequential circuit. So I even though I've encoded it, since I didn't need a catch-all, I like putting a catch-all. It says something to the human readers on this. So that's it for part A. I'm going to do one more problem in part B, and then that's it for this chapter. Now keep in mind there is a nice cheat sheet for this, or for state machines in general. Like I said, I follow the cheat sheet, and or particularly I just cut and paste from a given solution.